let us learn about boost DC-DC converter or step up DC-DC converter. This converter also has two switches, one inductor and one capacitor. Vin is the input DC voltage source, R is the load resistance, and the voltage across the capacitor is the output voltage VO. And we are also given the switch states, the combination of switch states, S1 on and S2 off for a duration of dTs, where d is the duty ratio, and for the remaining interval 1 minus dTs, S2 is on and S1 is off, and Ts, the sum of these two intervals is Ts, which is the switching time period, and it keeps repeating. So we have two state combinations. So what we do is we draw the circuit as we have done in the case of buck converter, and we apply KCL and KVL, and we write the resulting equations in both intervals. That is what I have shown. I have shown the equations here. You can draw the circuits and verify these equations. So when S1 is on, S2 is off, VL, the voltage across inductor, is equal to Vin, and output voltage is obviously the voltage across capacitor, but the output current IO, this is IO, and IO is equal to minus IC, or the capacitor current is equal to minus VO by R. And in the other interval from dTs to Ts, S1 is off, S2 is on, so the voltage across inductor is the difference between Vin and the capacitor voltage, and S2 is assumed to be ideal, so the drop across S2 is 0. So Vin minus VO will be VL, and again if you apply KCL at this node, IC will be IL minus VO by R in the second interval. So if you look at the voltage across inductor, the waveform of voltage across inductor, it will be Vin in the first interval, which is dTs, and Vin minus VO in the second interval. And by our small ripple approximation, this small VO becomes, lowercase VO becomes capital VO, uppercase VO, because we are assuming that the ripple in VO is very small, or the capacitance is adjusted, it's so high that VO can be approximated by its average value. We are talking about periodic steady state, and in periodic steady state the average voltage across inductor should be 0. So that means the area under the positive part of VL should be equal to the area under the negative part, and of course both areas should be opposite in sign so that the integral adds up to 0. So that will clearly tell us that this VO should be greater than Vin. That means the average value of output voltage should be greater than Vin. But what is the average value of output voltage? Let us try to find out. The average output voltage can be found by using the principle of volt-second balance, because the volt-seconds across inductor should be balanced in periodic steady state. So if you apply that principle, Vin dTs plus Vin minus VO times 1 minus dTs will be equal to 0. So that will give us the relation between VO and Vin as follows. VO is equal to Vin by 1 minus d, and the duty ratio is between 0 and 1. So if your duty ratio is 0.5, that means if switch 1 is on for half of the Ts, half of the switching period, and switch 2 is on for the remaining half, output voltage, the average value of output voltage will be double the input voltage. Similarly, if you have a duty ratio of 0.75, it will be 4 times the input voltage. So this equation theoretically tells us that as d approaches 1, we can actually produce larger and larger output voltages. It's like infinite gain, but that is only in theory. In practice there are some limitations. We will understand the limitations soon. In fact, we can also think about it intuitively. D is equal to 1. What does it mean? That means S1 is always on, S1 is always on, S2 is never turned on. So if the capacitor has 0 initial voltage, how will it charge? It will never charge. And we are connecting a voltage source across inductor directly. So the output voltage will definitely be 0, will remain 0, because the input has not been connected to output at all. And on the input side, you have a constant voltage that is appearing across an inductor. That means di by dt is positive, and that constant voltage is positive. So di by dt is positive. So the current keep on increasing and it will destroy the inductor. So d has to be always less than 1 in this case, and when d is less than 1, the relation V in by 1 minus d is valid as long as the components are ideal. You don't have switch drops, voltage drops across switches, you don't have series resistance of inductor, you don't have series resistance of capacitor, but when you include all of them, they will actually reduce the voltage gain also. However, in principle, the output voltage, the average output voltage has to be more than the input voltage. That is why it is called boost converter. And how does the inductor current vary? The inductor current waveform is shown in red color here, and assuming some initial value of IL, because we are in periodic steady state and the inductor current is basically the integral of inductor voltage. So the integral depends upon the initial condition. So assuming that we have an initial condition here, the current through inductor will rise linearly because the voltage across inductor is positive and constant. So it's a linear rise of inductor current, and then in the next interval again the voltage across inductor is almost constant but negative, so the current will linearly fall, but it will reach the same point as we started at t equal to 0, because in periodic steady state the volt seconds are balanced, and it will keep on repeating. So inductor current will again be a triangular waveform, and we are considering the continuous conduction mode. So we will not have the state of both switches being off. And delta IL is defined as the peak to peak value of inductor current, and capital I subscript L is the average value of inductor current. The peak to peak value of inductor current delta IL can be easily calculated by calculating the slope of the rise or fall. So if we look at the slope of the rise in the interval dTs, delta IL by dTs is equal to V in by L, because the voltage across inductor is V in, and that gives delta IL as V in times dTs by L, or V in can also be expressed in terms of VO, because VO is V in by 1 minus D. So it will be VO times 1 minus D into dTs by L. So for a given output voltage, which is usually the case, the input voltage can vary, but our appliance or our load which is connected at the output of this boost converter may need a regulated output voltage. So irrespective of input voltage variation, we will be maintaining the output voltage constant. And how do we do that? By adjusting appropriately the duty ratio. So for a given output voltage and switching frequency and value of inductance, the peak to peak ripple in inductor current will be maximum when D is equal to 0.5. But of course that 0.5 has to be in the range of duty ratio of operation. And how do we calculate the average value of inductor current? We can calculate the average value of inductor current through charge balance in capacitor, or we can also calculate through the power balance. The average input power is equal to the average output power. So PO is equal to P in. So that means VOIO is equal to V in into IL average, because the input current or the current drawn from source is same as the inductor current. Since the converter is lossless, this statement is true. So it will be V in into IL, and if we substitute the expression for VO in terms of V in, it will give us the expression for IL as IL is equal to IO by 1 minus D. And what is IO? That is average current at the output. Output voltage is almost assumed to be constant because of the small ripple approximation. So it will be VO by 1 minus D times R. Remember, we have not drawn the waveform of output voltage yet. We just know that the average value of output voltage is V in by 1 minus D. So if we need to draw the waveform of output voltage, we need to know the current through the capacitor so that we can integrate the current waveform and get the voltage waveform. And how does the capacitor current look like? The capacitor current is minus VO by R in the first interval, and strictly speaking it will be an exponential fall, but we have assumed that the capacitance is very large or chosen to be large enough so that output voltage is almost constant. That means the exponential fall is negligible, the decrease in voltage is negligible. So with that, the capacitor current will be a constant value, it's minus VO by R, it's an approximation. And in the second interval, it will be IL minus VO by R. So IL is drawn in the red color, and you subtract the VO by R, the average output current from it. That will give you the capacitor current waveform, and it will keep repeating. And as we already know that the area under this negative part of capacitor current waveform and the positive part of capacitor current waveform are equal because we are in periodic steady state and the charge balance has to be maintained across a capacitor. We are ready to draw the output voltage waveform now. We will just integrate the capacitor current and get the output voltage waveform. So starting from an initial condition, the output voltage, the capacitor voltage has to fall ideally because it is just an RC circuit and that fall is exponential. Yeah, we are contradicting the small ripple approximation. Like if you look at the waveforms, they indicate that the capacitor current we have drawn to be constant in the same interval, and that constant we also told that it is minus VO by R. And on the other hand, we are drawing the voltage across the capacitor to be varying. So here is the substantiation. We will exaggerate the voltage waveform of the capacitor and actually look at what is the peak to peak ripple and make sure that it is very small when compared to the average value, so that all our previous predictions will be correct. That is the way to understand these waveforms. Now in the second interval, the capacitor voltage will again rise because the current through the capacitor is positive, and in the subsequent interval it again fall, and it will keep on happening because we are in periodic steady state. And what is the peak to peak value of this capacitor voltage or output voltage? If you look at the first interval, the change in voltage is minus delta VO because it's a fall. So minus delta VO by DTS is equal to minus VO by RC. RC is just C dV by dt in the differential form, in the difference form. And what do we mean by our small ripple approximation in this case? Delta VO by VO is much less than 1. It means DTS is much less than RC. That means the RC time constant is much larger than the switching time period. So when that is valid, our small ripple approximation is valid and all our analysis holds good. And the input current waveform will be exactly same as the inductor current only. So the input current waveform is smooth in the case of boost converter, unlike the buck converter, where it was going all the way from 0 to the peak value of inductor current. The waveforms that were drawn on the slide are under periodic steady state, but if we start from initial conditions as 0, like 0 initial conditions, this is how the current waveforms and voltage waveforms look like. The first waveform is the inductor current waveform. It will start from 0 and it will rise. And the third waveform is the capacitor voltage waveform. As the output voltage increases, the negative voltage that is appearing across inductor will also increase, as seen from the second graph. That is how the periodic steady state is reached. So we have considered a 40 volts input voltage source and a duty cycle of 50%. So the capacitor voltage, output voltage is almost 80 volts. The average value of output voltage is almost 80 volts as expected. It will be double the input voltage. And now comes the switch realization part. So we need to look at the switch currents and voltages. That means the current carrying capabilities and the voltage blocking capabilities, so that we can replace the ideal switches or generic switch representations with the actual MOSFETs or diodes. So we look at the first interval, S1 is on, S2 is off. So S1 is on, the current through S1 is same as the current through inductor, and S2 is off, the voltage across S2 with the defined polarity VS2 is V in minus VO, which is less than 0 because the output voltage is greater than input voltage. We are talking about periodic steady state. And in the second interval, when S1 is off, the voltage across S1, that means the voltage that is blocked by the first switch, is equal to the output voltage. Sorry, there was a mistake and it is corrected now. So when S1 is off in the second interval, VS1 is equal to VO, and S2 is on, and the current through S2 is same as IL, the inductor current. So if the inductor current is positive, in the second interval, the current through switch S2 is positive, and in the first interval, the current through S1 is positive. So with these current carrying and voltage blocking capabilities, we can say that S1 can be replaced by a MOSFET because it has to conduct in this direction and also block a positive voltage. And for the case of S2, diode would do the job because it has to conduct in this direction but block a negative voltage defined with this polarity. So that is how we can realize the boost converter using practical switches. Let us also have a look at the effect of non-ideality. One non-ideality is considered here, which is the resistance of the inductor winding RL. So this drop across RL, IL, RL comes in the KVL equations in both the intervals. So if we again follow the volt-second balance principle and the integration of voltage across inductor, if we equate it to 0, we get this relation, VO by Vin is equal to 1 by 1 minus D into 1 by 1 plus RL by R into 1 by 1 minus D the whole square. So if RL by R is 0, then VO by Vin is 1 by 1 minus D, and the variation of the same is shown here, the first plot. For any finite value of RL by R, we can see that this 1 minus D the whole square goes into the numerator and it causes the output voltage to drop to 0 when D is equal to 1. As the value of RL becomes more and more significant, or the ratio of RL by R increases, the voltage gain gets limited even at lower duty ratios. That is why the boost converters are used typically in the low duty cycle range, maybe like 0.3 or 0.4 up to 0.6, definitely not beyond that. So the gain, the voltage gain, which is the ratio of average output voltage to the input voltage, is typically limited to 2.5 or 3.